Hello, my name is Bob Stewart. I'm from the University of Strathclyde, and in this short 20-minute session I'm going to give you an introduction to software-defined radio and how that relates to the RFSOC device. So in this presentation we're going to talk about software-defined radio with the RFSOC. Just as an overview of what we'll discuss, we will of course remind ourselves just what we mean by software-defined radio. We'll take a look at the simple radio frequency spectrum, mainly what we might call the low and the mid bands below 4 GHz. We'll remind you of the Nyquist sampling theorem, the fundamental of digital signal processing. We'll then look at what are the prospects for sampling the RF spectrum and this concept of first and second order Nyquist zones that we can do with the RFSOC. A quick look at some of the key software-defined radio and DSP components of the RFSOC, and we'll then summarise and conclude. So software-defined radio, well, it's when software replaces hardware. And let's have some examples of that then. An analog mixer, well, that will become a high-speed arithmetic multiplier, multiplying samples together. An oscillator, an analog sine wave oscillator, well, that becomes a lookup table in memory. An amplifier, a gain stage, might just be a scaling factor. And some RLC bandpass filter, well, we could do that with a digital filter of a specific frequency response. And multiband channelizers, that's a bank of digital filters, or maybe some efficient processing using FFTs, fast Fourier transforms. And of course the MAC layer and some of the other parts of the PHY layer, well, we will be running that on software implemented on FPGAs and their processors. In some of the slides, there's actually notes below the slide, so I won't focus on these in this presentation, but if you're watching in video, you might want to freeze frame for a little bit more detail as you watch. So the RF spectrum, if we look at what we have going from low frequencies, well, there's a very well-known FM radio down at 100 or so megahertz, then some aeronautical frequencies. Then in the UK, this is a UK representation, we've got the broadcast or digital audio broadcast radio. At 433, we've got our garage openers and some of our short-range devices. Then we've got the television band between about 400 and 700. And then here's a 5G band at 700 in the UK and some other countries, and so on. And as we go higher, we have radio navigation, space to earth, SATCOMs, more mobile. And then here's GPS above 1.5 gigahertz. So lots of interesting frequencies, and of course many more that I've not represented on this simple diagram. And if we go a little bit higher, let's go up to 1.8 gigahertz start. And again, we can see, there's more interesting mobile, the old 3Gs there, and satellites, Earth to space. And then, of course, the very well-known Wi-Fi and Bluetooth at the 2.4 gigahertz band. And going even higher up to 3.5 gigahertz, we can see another 5G band in many countries, and the US has got CBRS. And if we go all the way to millimeter waves at 26 gigahertz and above, then we're expecting 5G comms there. That won't be a focus of what we talk about in this course, but nonetheless, there's future comms at millimeter waves coming just round the corner. So, reminder, the Nyquist sampling rate, the fundamental signal processing theorem. There's a number of ways interpreting and presenting, but essentially you take a signal of a given bandwidth, and as long as you sample at greater than twice the bandwidth, then you will retain all information in that signal. Now, of course, you might be doing some quantization, and we're not really focusing on the quantization effects here. We're just talking about the sampling theorem. Nyquist said you retain all information if you sample at greater than twice the signal bandwidth. Now, sometimes people say that Nyquist sampling rate is sampling greater than twice the maximum frequency. Now, of course, that's only the case if your signal maybe starts round about baseband or 0 Hertz and goes all the way to some maximum value FB in this case. So sometimes you'll hear Nyquist sampling theorem is twice the maximum frequency, but it's more correctly twice the bandwidth of the signal. And for more detailed reviews of the capability of the RFSOC, that's quite an important point, because many of the radio frequency signals we will look at are in fact band limited, like a 40 megahertz mobile radio channel or a 10 megahertz 4G channel. So that's something we could focus on when you do your actual real designs and implementations. Now, sample rates. I've been around for a few years doing signal processing, and I can remember the excitement in the 1980s when we started sampling digital audio. 44.1 kilohertz, just amazing doing this on a computer, on a PC, and that was the start of the audio revolution. If you think where we've ended up today, well, we've gone through kilohertz sampling to megahertz to tens of megahertz, and we're now up here, between 1 and 10 gigahertz with the likes of the RFSOC device. And of course, we've also got multi-channel. So in just a matter of a few tens of years, we've gone from hundreds of kilohertz, and we're now up there at gigahertz sample rates. Just amazing. And that, of course, is almost equivalent to things like Moore's Law, just this increase in clocking speed in the analog to digital and digital to analog sample rates. So let's consider again sampling at a sample rate of 4 gigahertz. We'll choose 4 gigahertz because that's approximately the rate that David will be using in some of the examples on the RFSOC 2x2. So if we did sample at this rate, then, according to simple Nyquist, we can start down here at baseband. We'll get the FM radio, the broadcast, the TV, the 5G, and so on, all the way up to FS over 2. The Nyquist sampling rate will give me 0 to 2 gigahertz. And if you wanted to go above this and you wanted to get 2, 2.5, 3.5, well, it would appear we cannot without going to a higher sample rate. But actually we can, and that will be the innovation of using the second order Nyquist band. So certainly up to 2 gigahertz looks pretty much straightforward. So here's a sketch of a very simple RF software-defined radio system, first order Nyquist, and we can see that of course we do need front-end anti-alias type filters. So we've sketched these cutting off around about 2 gigahertz. So the energy that goes into the ADC and comes out from the DAC is in the range 0 to 2 gigahertz. So we have our first order Nyquist system. And in here, of course, we're doing all of our digital signal processing, all of our interesting radio implementations. Now, the second order Nyquist zone. So let's just think about what we've done here. So we've done a low pass filter, and we try and remove the energy above 2 gigahertz. And that's the classic first order Nyquist zone that we've been doing in signal processing for many years in many different domains. But what about if we actually put on a front-end analog bandpass? And let's retain the 2 gigahertz to 4 gigahertz band. And if we do that, we remove the energy from 0 to 2 gigahertz, and of course we remove energy at higher frequencies as well. And when we sample this band, as we'll look at a little bit later in another presentation of mine, this will alias down to baseband. And this energy will now appear down here at the lower band 0 to 2 gigahertz. So frequencies have moved from one value to another, but that's easy to track. And well, we can use the second order Nyquist zone, and the RFSOC will use the second order Nyquist zone. And once again, this is something that David will show you in some demos coming up. So let's just sketch that, the concept of using the second order Nyquist zone. So at the front, you will need appropriate, bandpass analog filters to capture the band of interest, the 2 to 4 gigahertz. This energy will then alias after you've done the sampling. And once again, we'll do our digital signal processing to do all of our radio type implementation. So if we look at the Zynq RFSOC again, let's look at the kind of the core components we have for software-defined radio. So it's a system on chip. So there's many different components that we can see. We have a processing system, and we'll see this processing system consists of various ARM cores and other processors. We have our programmable logic, and we've got our up converters and down converters. We've got some forward error correctors. And if you think about it, we've got to get data on and off this device fast. So we have a number of different transceivers and GigE and CPRI for connecting radios. So that's a kind of high-level signal processing SDR view of the RFSOC. And remember, the RFSOC, it is an FPGA, and it's an FPGA with RF DACs and RF ADCs integrated onto the same piece of silicon. And if you consider what else is in the market, well, you can just get yourself a kind of a classic Zynq MPSoC device, and you can connect that externally to front-end radio chips, ADCs and DACs, and of course a two-chip solution is very common, and for various engineering reasons, sometimes that will be a solution that people will choose. But what we're interested in sharing is the innovation of the RFSOC with the programmable logic, the processing system, and the RF DACs and ADCs all on the one piece of silicon. Multiple channels. Well, we're not just got one ADC and one DAC. We have up to 16 in some systems. So for this single chip RFSOC, that brings all sorts of interesting radio opportunities, working with multi-band radios and on different input channels, or MIMO systems or MIMO systems with multiple antennas, maybe 4x4 or 2x2 or whatever it might be. And of course, again, using multiple channels for beam forming and beam steering. So lots of applications, of course, that we're doing with other devices, but now very applicable to the capability of the RFSOC. So in the processing system, Patrick discussed this a little bit earlier on, but we have a number of ARM cores, A53s, and dual-core ARM R5s, and many of you will know that the ARM is widely used in mobile and indeed wireless applications. And this processing system, these are processors on the system on chip, and again giving us all sorts of classic functionality that you would get in any processing system. In the programmable logic, well, that's the classic part of an FPGA that, of course, we've been using for many, many years. And anyone who's been involved in the FPGA signal processing market for the last 10, 15 years, well, we didn't always have the processing system, and we certainly didn't have the D2As and A to D converters. So the programmable logic, well, we've got high-speed transceivers on there. Very important. We've got to get a lot of data on and off the device. We've got lots of configurable logic blocks, and depending on the device you buy, will specify the number of logic cells in that particular device. We have a tremendous number of DSP slices, which are essentially evolved multipliers, multiply accumulate units, in fact, almost mini processors. And once again, if you go back maybe 25, 30 years, a DSP processor had one multiplier on the device. We've now got many thousands, clocking at gigahertz, so an unbelievable level of signal processing available. Hence, again, software-defined radio. And we've got block RAM and ultra RAM, places to store intermediate data as we do the processing. And there's also efficient ways of connecting the processing system to the programmable logic so that data can be passed efficiently between both. So lots of resource and capability for designing our software-defined radio systems. And there's a quick look at one of the DSP 48 slices. So on the slice, we have tremendous DSP functionality with a multiplier, and we've got pre-adders, and we've got post-adders, and so on. And you've got many thousands of these that you can configure on your single RFSOC device. Also, essentially part of the programmable logic are the RF down converters and up converters, so the DDCs and the DUCs. So on the transmit side, as you're taking baseband information and you're taking it up to a higher frequency and onto essentially an RF carrier, you'll be using an oscillator, which is actually a numerically controlled oscillator. So again, a form of lookup table. We'll have a number of stages of filtering as we do this upsampling, or cosine and sine oscillator, and then that data will be sent to the so-called real world as RF through the RF DAC. And at the other side, we'll of course have the direct digital down converter, the DDC, so receiving a signal, and we receive that signal and we'll then mix down to the baseband, and I'll tell you a bit more about that later, a number of filtering stages, and usually we have IQ data and we send that off for processing. In the programmable logic, there's also forward error correction. So if you're familiar with communications, you'll be aware that very often we'll add redundancy to the symbols of data we will transmit, and this can be used for error correction. And at the receiver, that's a very intensive computation process. So rather than use processing cycles for that, what we have in the RFSOC are some SDFEC blocks, some hardware-coded blocks to accelerate maybe turbo coding or LDPC coding, and again make the architecture as efficient as possible when you're working with radio implementations. So the SDFEC blocks, LDPC, turbo coding, and various other accelerated implementations. And what you will actually select will be a function of whether it's 4G or 5G, and so on. And of course, you may choose not to use these for some good engineering reason. So over the last few years, we've also seen the evolution of disaggregated radio for SDR. And the thing about disaggregated radio is a simple idea that we've taken the processing that we're required to do for a software-defined radio system and split it into a couple of blocks, so disaggregated or separated. So at the top of the radio tower, we have the radio head, and that's sometimes called the lo-fi, and the centralized processing at the bottom of a mast or in some central location. We might call that the hi-fi, the higher, the physical layer at the kind of high level. And once again, deciding how we split the processing is part of the software-defined radio design. So let's try and make a little bit more sense of that. So, there's your tower, and there's your antennas at the top of the tower, and maybe there's one of your boxes near the top of the tower, and your short RF connectors to the antennas. And inside that box, well, maybe we've got an RFSOC. And that RFSOC is doing a lot of pre-processing. It's doing the analog to digital and digital to analog conversion. And coming off the tower, we go to what we might call the baseband unit at one time, and that could be at the bottom of the tower, or of course that could be in some centralized location, or it could be in a cloud server. So we see the lo-fi and what we might call the hi-fi as both opportunities for the RFSOC here at the top of the tower, and also here in the baseband unit, where things like the SDFEC, the forward error correction, absolutely would quite like the power of the RFSOC to be available. And of course, this one here does not need to use DACs and ADCs. So there are special versions of the RFSOC that actually don't have the DACs and ADCs. So that's not quite ORAN I'm showing you, but if you've come across OpenRAN or ORAN, well, the idea is that let's do a split in the computation, and let's get everyone doing the same split, so that in the near future we will have interoperability of remote radio heads with someone else's baseband unit, or the lo-fi with someone else's hi-fi layer. And that's one of the ideas behind the ORAN opportunity. And of course we can maybe put that in a more topological representation here, multiple radio heads, going to some Base station hotel is another terminology sometimes used in the older days. And in that base station hotel, you're doing all of your hi-fi computation, and another great place for an RFSOC. So RFSOC advantages for radio, well, we've touched on some of these, and we'll now see a lot more in some of the demonstrations and a little bit more detail in the signal processing coming up from myself and from Louise. So, well, very wide RF bandwidths are available, so we will be digitizing at 4 GHz. We will be using the first and second order Nyquist zones. We can support many different radio architectures, all digital or digital to IF, and we can cover many different frequency bands. We can do multiple channels with the RFSOC, up to 16, in and out in some of the chips that are members of the RFSOC family. And again, it's a single chip solution. So one chip is doing all of the software-defined radio and the kind of analog front end. And we've got integrated DUCs, digital up converters and digital down converters, very powerful blocks that allow very efficient ways of channelizing and selecting different frequency bands. And again, Louise will give a bit more information on that in upcoming sessions. So, a few conclusions. So what have we done in this presentation? Well, we have introduced the RFSOC platform and described some of the key features from a perspective of radio design and direct RF sampling. We've also noted the high value supported sampling rates we can cover, so up to, again, a few gigahertz, and some of the radio standards that we can therefore directly digitize. We've looked at some of the basic features. We haven't described them yet, but digital up converters, down converters, forward error correctors, some of the processors, and all of these will come together to build our software-defined radio. And coming next, a little bit more exciting, and that David will start showing you the RFSOC 2x2 in software-defined radio action. So that's the end of this presentation. Thank you.